facciamoci sto selfie qua con la platea, dai, così sembra che lavoriamo. Sì. Apri.
Alza lo schermo.
Troppo bella.
Hey everyone. All right, mic is on now. Thank you all for coming. If you're striking in the back, come on in. There's plenty of room. In order to make sure there's plenty of room, if people are trying to find a seat in your row and there are empty seats in the middle of your row, squish in, make sure there's room for everyone. We don't want people standing in the back. For those of you who don't know me, my name is Dan Schaefer. I'm a software engineer at Facebook, and along with Lee Garner and Nick Strock, helped create GraphQL about 7 years ago. It is unreal to be here. I feel like I say this every time because every time it's true.
You know, looking around the room, it was 200 people 2 years ago, 400 people last year, 800 people here in Berlin today for our GraphQL conference. This doesn't happen without you, the community, so thank you all for coming. So one thing I do want to note to kick the conference off, you know, this is a community. It's a community that we're building. It's one that we're building together. We do have a code of conduct for this conference, and that's there to make sure that this community can continue to be a place that welcomes everyone who's interested in GraphQL and can continue to grow as it has. So the code of conduct exists. If you see anything, you can talk to someone wearing a GraphQL t-shirt. There's a email address here. There's a phone number that you can send a WhatsApp message to. This is really important. It's the only way we're going to keep this community growing. And that's me. Cool. So to kick off today, I'm going to grab the slides. This is GraphQL. I think I'm not giving anything away there. But what I'd like to talk about today is what GraphQL was before GraphQL. Because I feel like at this point, the story of GraphQL, we've told it a bunch of times. You know, we've told that story of the initial prototype in February of 2012 and hacking in the corner and trying to figure out what this was going to be, and eventually shipping it in the iOS app in August, the open sourcing in July of 2015, and then, of course, where we are today. But the story that we haven't told quite as much, and the story that I think is really important to understand GraphQL and why it exists and a lot of the decisions we made, is that prehistory. It's the probably 4+ years leading up to 2012, because a lot of the architectural decisions we made there really made GraphQL possible. And if you look at GraphQL today, you can see the effects of those decisions on the technology and on the way it operates. And so before I dive into this, I do want to caution. This is not the one true way of using GraphQL. This is not the way to do it, and if you're not doing it, that's crazy. This just happens to be the Facebook server architecture in 2012. But the reason I think it's worth talking about is this was the Facebook server architecture in 2012. GraphQL was built for this architecture. And more importantly, I think there are some good ideas in here. Some ideas that I think were good in 2012, some ideas that I think are good today, and some ideas that I think really sort of transcend just building a GraphQL server at Facebook in 2012 to building things in general. So that was a little bit abstract. Oh, these are going to be some good ideas. If you're working with GraphQL today, why does this matter at all? Like, what sort of things in GraphQL does this inform? Well, I'm going to go back a little bit to philosophy, because I actually think this philosophy really resonates with me, and I think it sort of explains some of how GraphQL operates. There's a quote from Doug McElroy. This is the Unix philosophy: write programs that do one thing and do it well, write programs to work together. And when I think about the way that GraphQL operates at Facebook, and when I think about the way that almost the spec is designed, there are a lot of questions that it very specifically does not answer. It does not have a canonical way of doing authorization or efficiency or caching or rate limiting, which are all really, really important questions. And it's not that it ignores these. It just doesn't address them. And the reason why it doesn't address them is because these were already answered by Facebook's server architecture in 2012. And so these concerns were not specific to GraphQL. GraphQL was not designed to solve these. GraphQL was designed to compose with a solution for these that we anticipate would either already exist or that you could bring into existence. And so that's a little bit why I want to talk about this era, because it does help answer all of those questions and explains how we were able to answer them without GraphQL, and therefore how GraphQL was able to evolve as a rather small piece of technology in the stack, one that's critical, but one that doesn't necessarily try and answer every question. It tries to answer one question and one question well. And when I think about this era at Facebook, I really think of three key architectural developments, three key principles that both informed how we built things and that we emerged with from building things. And those are these three. This idea that data requirements form a tree, the idea that you need to design around asynchronicity, and our desire to strive for single sources of truth. I'm going to walk through all three of these and give an example of how this emerged in Facebook and really build up that stack in a way that hopefully by the end you'll be looking and saying, oh, I can see how GraphQL emerged from this. So let's start with the first one, this idea that data requirements form a tree. And throughout this whole example, or the whole presentation, I want to have an example. I want to make sure we're building something concrete. So this is a very, very basic sample app. It is a sample app that has a user, and it has a best friend, and it has a list of friends and their best friends, and I don't think I'm giving anything away here. I'll have Lee do a polish pass on it at some point. But this is the initial working design. It's at least functional. And if we were going to try and build this, how would we do it? Well, we might just say, let's throw it all into a SQL table. And we'll query the data, and then we'll build the view from there. And it would look something like this. We're going to fetch the user's name. We'll fetch their friends. We'll fetch their best friend. We'll join the friends on that. And then we'll go and fetch their name and their best friend's name. This would work. We could build this. By the way, I'm also not a SQL engineer. That almost certainly isn't valid SQL. It's fine. The concept is there. So why wouldn't we do this? We're done, right? We've built it. End of presentation. Well, there are a couple of things about this that just don't quite click with me. The first one is a little bit these joins, because this assumes that we can efficiently run the joins across all of this. And if this is all in one SQL database, that might work. But you can imagine as this grows to, as a hypothetical social network, billions of users, maybe we're not just running one giant SQL database. Maybe we're going to need to shard this across multiple DBs, and suddenly these joins aren't looking quite as trivial. But that's a very technical answer for why we shouldn't build it this way. I actually think there's a conceptual reason why we wouldn't build it this way too, which is that sort of sequence of joins, that sequence of tables and how they connected, isn't how I think about this app. When I describe this app to you, if I were going to describe it, I would say, we're going to fetch the logged in user. That's me. And then we're going to go and we're going to fetch that person's friends, and we're going to fetch that person's best friend. And then for each of their friends, we're going to fetch their name. And then for each of those friends, we're going to fetch their best friend. This is how I start to think about the app. This is sort of what gets created. And it translates fairly reasonably into an underlying query. I'll use Redis here as an example, also not a Redis engineer. But you can imagine the get going out, a get and a range, a bunch more gets, and a bunch more gets. And we can see, if we were building it this way, what would emerge. What are the actual Redis hits that we're going to do? And one of the nice things that emerges from here is we realize that our data requirements form a tree. When we think about our data requirements, when we describe our data requirements, that's the shape that they take. And I don't think that's a coincidence. Because when we think about our apps, when we think about our views, when we think about our interactions, they very often also form a tree. And that tree doesn't just describe the shape of our app. That tree also describes our data fetching strategy. And if I go back to this, there are actually some really nice optimizations that we can do here. You can imagine these 5 friends, the ones that we're fetching all at the same time. There's actually no reason why we would do 5 round trips to a DB in order to fetch them. We have all 5 of those IDs at once. So it'd be really nice if we did that in 1 round trip. And we would use something like an mget in Redis. And then similarly with these 5 friends, we can do the same thing, and we can optimize the heck out of this thing. And if you're familiar at all with data loader, this is exactly what data loader does in JS. And the reason data loader exists is because there was a corresponding abstraction within Facebook called loader. And we were talking with folks about GraphQL, and they're like, well, how do you solve this problem? And our answer was, what do you mean, how do you solve this problem? This problem's already solved. There's an underlying abstraction. There's a thing that GraphQL can compose with in order to do this well. And there are a bunch more interesting optimizations that we can do here. And one of the talks I'm really excited about for later in the next 2 days is Andy's talk, because he's going to dive really deep into this in great detail, including how the GraphQL spec addresses it. But one really critical thing, before we even dive that deep, because I'm just touching the surface here, is this layer of the tree. Because this layer of the tree, we're trying to fetch the friends, and we're trying to fetch the best friend. And we don't need to block on one before the other. We don't need to wait for the friends to come back to go to the best friend. But these are also 2 different queries. This isn't really a data loader style problem. How exactly are we going to solve it? And in particular, how are we going to solve it in actually writing the code? Because that's one thing I've completely elided so far. We haven't had actually written code to do this data fetching. And the realization that we had repeatedly is that we have to design our servers around asynchronicity. That is just critical to making sure that our servers are going to be efficient and that we're going to be able to build the app that I described using the efficient queries that I described. One challenge we ran into, this is 2008, I think is where I started that timeline, so we were using PHP 5. PHP 5 in 2008 did not have good asynchronous primitives. And so we made do. So let's imagine this is the query pattern we're trying to get. This is sort of the thing we want to see in our Redis logs if we got everything right. What are we actually going to write in 2008 era PHP? Well, our initial step would just be this. Just get the data. And this, of course, will do 13 round trips, because every time we call a get, we're actually going to go and hit this get as a synchronous call. So what could we do instead without asynchronous primitives? Well, one thing we could do is we could say get doesn't actually issue the round trip. Get queues up the round trip, and then I'll add a magic function, call it dispatch, and that will actually do the round trip. And so you queue everything up, you call dispatch, and that actually goes and hits Redis. This seems kind of concocted and seems kind of fake. This is pretty much what our code in 2008 would have looked like. This true that's at the end, that says, hey, that get call that was supposed to be synchronous, don't make it synchronous. Make it async instead. And that additional parameter, that third parameter, is a reference variable that when it actually gets fulfilled will get filled in. And if this seems confusing, don't worry, it gets worse. But I want to really strongly emphasize, this was not hypothetical. This is actually what we did. Because asynchronicity was that important to us. We knew we had to do this in order to make the app run efficiently, and so we did. It wasn't good. So we iterated, and we improved. And we came up with something that we called preparable. And a preparable basically said, okay, instead of having a single magic function that says dispatch everything all at once, the preparable says, I'm a function that has multiple stages of fetching, so I'll put the first stage in case 0 of a switch statement in a magic function. I'll put the second stage that requires the first stage to be done in stage 1. And again, you eventually get used to this, but not really. But this was something that we used very, very heavily throughout the app. I mean, it's something we talked about on Quora. It's up there. And it's something that we gave talks about. This is a slide from a talk that we gave on preparables in 2011. And when I say we here, I'm using, a little bit the royal we and a little bit we as Facebook. But I also can use it as we, the creators of GraphQL, I guess, because this talk was given by Nick Schrock in 2011, talking about preparable and talking about really a lot of the things that I'm covering here. And I'm starting to hint at, the evolution of GraphQL, what created. It didn't emerge from sort of this primordial void. It emerged from these problems that we were solving in Facebook server architecture, problems like asynchronicity that we were solving with preparable. So going back to preparable, unless you worked at Facebook, this probably looks rather unfamiliar, with one exception. If you ever played with Regenerator, which allowed you to use sort of function stars in JavaScript, and it would effectively compile it into something that didn't use function stars, this is what the output looked like. Looks a lot like preparable, and that's not by coincidence. Really, all preparable was a way of implementing generators, which you can sort of simulate async functions with, when you didn't actually have generators in the language. So in conclusion, we were taking our functions, we were turning them into objects. The state of those objects was literally what we now consider the output of a compile step, because who would write this manually? And this was the state of the art in 2010 or 2011. And I want to further emphasize, this is exactly what we did. We did this because asynchronicity was still that important. We had to do it in order to make our server run the way we wanted to. We spent so much time iterating on these async primitives. And the good news is you don't have to, because all we were doing was building async await. And async await exists now, and virtually every language that I would consider using for a server has async await. And if that sounds like a slight dig at Python or Ruby, okay. And why do I like async await so much? Why do I think it's so good? Well, this code that we wrote, that's pretty much what we wanted to write. It's pretty good. I can read that code. I mean, this is a hypothetical app with no designer, and that I just explained 10 minutes ago. You can read that code and go, yeah, I know what that does. And that's a really important principle, and it's one that certainly the memcache dispatch and the preparable did not have. Well, with async await, you still have that. You're just fetching the data. You're bundling the things you want to do in one round trip. You can compose these things as you like. It's just pretty. It's really nice. I like it. And I'm going to violate the laws of sort of time here, because I'm supposed to be talking about 2008 to 2012, and I might be dating myself, but I'm going to do like a season 3 Lost thing where we just like flash forward, and we're going all the way from 2008 to 2012 to last month. Because I said async await's really good, and async await is really good. I like the code a lot, but this line never quite sat well with me. It feels kind of awkward. And it's not awkward in a slide format, because you can usually simplify it down, and this makes sense. But this is the equivalent of what it would look like in PHP. It's not that ugly. It's just dollar signs. But ultimately, your app grows. And you do more and more things with this function. And the function ends up looking a little bit more like this than you would like. And this is ugly. This is twice as many lines of code as it needs to be. You can't really follow what's going on. And I'm also doing that trick that speakers always do, where they show a bug on a slide and then see how many people spotted it while they were talking. Show of hands. It's there. I messed this up. I assigned the additional data to extra, and I assigned the extra data to additional. I don't know if I would have caught that in code review. I hope I would have caught that in unit tests, but I probably would have caught that in production, right? This isn't really what we want to be coding. And the good news there is we are trying to solve this in the hack language in HHVM with a new keyword, concurrent. that basically takes this code, which has a very subtle bug in it, and you would write this instead. And you would write these 5 things, and they would all run concurrently. And at least in my mind, the bug is very easy to spot now. It's like extra equals additional. It's like, yeah, that's wrong. I messed this up. So this is really cool. Why am I talking about this? I want to make it very clear, I had nothing to do with building this. I just think it's super cool. And in particular, I've been saying asynchronicity, it was that important. It was that important in that era. It is still that important that in 2019, we are still iterating on our server architecture to make sure that we get it right more often than we get it wrong. And so this is a lesson that I took away from that. You really want to design your server abstractions around async primitives. And one of the things that I've learned this hard way is anytime you design it around sync primitives, and someone decides they need to make it async in the future, which they will, that's really hard. It's a lot easier to call synchronous code from asynchronous code than vice versa. And so this is one lesson that I've taken away over and over again is if it can ever be async, make it async. And if it can't, you're probably wrong and it should be async anyway. And when I say you should design your server abstractions around async primitives, I'm talking a little bit from experience here because GraphQL did. So if you all turn your hymnals to the book of GraphQL, chapter 6, verse 4.2, we'll read responsively. This is the value resolution section. It's small type, but we all have it memorized, so it's fine. In case you don't, here it is. Yeah, that's small type. I'm going to need to go over here to read it. This one I'm going to read out loud because it's important. It is common for resolver to be asynchronous due to relying on reading an underlying database or network service to produce a value. This necessitates the rest of a GraphQL executor to handle an asynchronous execution flow. The GraphQL executor's got to be asynchronous because your server abstractions are going to be asynchronous. They need to be. Design it around asynchronicity. The final lesson that we learned was to strive for single sources of truth whenever possible. And I want to flash back to these 4 questions, because these are the 4 questions that I said I was going to answer at the start of the talk. I was going to explain how Facebook server architecture handled these. But I actually want to sort of look at these 4 questions and think of something different, because I didn't really answer them. But when we go to answer them, when we decide, OK, it's time we're going to solve these questions are really important. Authorization and authentication, you got to get it right. You're looking at caching? If you don't get caching right, is that going to take down one of your DBs? Right? You're trying to detect people who are spamming. You've got rate limiting. You don't want to get that right 90% of the time. You want to get it right all of the time. And if we always want to get things right, we only want to write them once. Right? If we wrote it twice, one of like 3 things happens in my experience. Either the first implementation's wrong, the second one's wrong, or they're both wrong. Very rarely are they both. You wrote it twice, and you happen to get it exactly right both times. And so the solution that we had at Facebook here, these single sources of truth, are what I would call smart data objects if I were speaking in generalities. If you're ever talking to a Facebooker and they sound super obsessed with Lord of the Rings because they're constantly talking about Ents, they might be obsessed with Lord of the Rings. They're almost certainly referencing these objects at Facebook. We know them as Ents. It's short for entity. And there's a lot to that abstraction, but it actually kind of fits on a slide a lot of the critical pieces, because this is really what one of those smart data objects would look like. It's just a class. In this case, it's in JavaScript, but we have it in PHP or in Hacklang. And that class has this static gen method. And this gen method returns a promise, asynchronicity is important, of a nullable smart user. It's saying, hey, if you tell me who you are, give me your viewer, and you give me an ID of a user, I will go and asynchronously get that user, and I will return it to you if I can. And this is important because that return it to you if I can, I'm fetching the user. This is where we can put a lot of those hard questions I mentioned earlier. We're trying to figure out where to put authorization. You put it here, because if this is the only way of getting a smart user, if you're in a language that lets you actually hide the constructor, then everyone who has a smart user object has to go through this. I mentioned caching. If you're going to integrate data loader into your stack, where would you put it? You can put it here. Rate limiting? How do you detect anytime someone's fetching a user? Well, they're always going through this method. This is our single source of truth for fetching a user. And then this object you can also sort of augment with additional capabilities. You can have these methods that basically say, hey, a user has a best friend. You should be able to fetch that thing. Again, an asynchronous promise that returns a nullable user. They might have a profile photo. Same thing. And notably, these smart data objects, all of their methods stay in that universe. They stay in the smart data object universe. And they use these gen methods as well. And so gen best friend, is that going through the single source of truth? Yes, definitionally. Because the only way to get a user is to call that gen method, so this method has to be implemented using it. So I know when I call this method, because it returns a smart user object, because I'm getting this, I know it's gone through the single source of truth. So this has two benefits. One of them is it avoids overfetching. I included that profile photo example. My mock was terrible. It didn't have any photos in it. I don't need to fetch that data for the mock. And if I'm using these objects, I don't. Because if I never call gen profile photo, I never run that asynchronous method, I never hit the DB. I've avoided overfetching. And secondly, and I think this is something that is subtle but really important, we have built-in preconditions. Imagine you don't have a single source of truth, and you're writing a method and you're like, okay, I want to get passed in a user, but you need to have already done a rate limiting check on that user before I can use it, because I'm not going to do it in my method. It doesn't make sense for whatever reason. So you would write that in a doc block. And all of your callers would read your doc block diligently and go, oh, I better do the rate limiting check or else something's going to go wrong. That's definitely what would happen in every code base I've seen. No. Like, you can write your preconditions in doc blocks, but you'll get it right some of the time, which isn't really what you want from a precondition. The nice things about these objects are you basically write your preconditions in the type signature of the method. If you give me a smart user object, I know you've rate limited it. And I know that because you went through the single source of truth to fetch it, and that thing did the rate limiting for me. And so it gives you a little bit of peace of mind, where you're like, hey, because I'm operating at this layer, I know that all the things I needed to do, all the things that needed to happen, have happened because the single source of truth guaranteed it. So this is where things might start to be looking a little bit eerily familiar. Because if I look at this class and I squint a little bit, it looks really familiar. It's kind of a GraphQL object type, right? Like this class. And these methods that I described that asynchronously maybe return another one of these types, those are just GraphQL fields that return objects. And that gen method, that's a root field, right? You put that on query. It's going to give you a user, given a viewer and an ID. It'll take an ID as a parameter. And this isn't by coincidence. The reason why this looks really familiar and why the concepts in GraphQL correspond so nicely to this is because that's what existed at Facebook in January of 2012 when we were building GraphQL. We had these smart data objects, and so we built GraphQL as a wrapper around them. And so one question that I'll occasionally hear is, okay, we have these resolvers. Are resolvers what should contain your business logic? And I generally advise no. Resolvers shouldn't contain your business logic. Resolvers should map to your business logic. If you look at the resolvers at Facebook, they are generally very, very thin and or non-existent, as you'll hear later today. Because we want the business logic to be in a single place. It's a thin API layer. And I think that's an important concept. The reason why GraphQL doesn't answer any of these 4 questions is not by omission, it's by design. So this has been GraphQL before GraphQL, sort of that initial 4 years, and it really goes even before that, but leading up to February 2012, that put us in a place where, you know, with 3 people sitting at a pod of desks trying to build this thing out in 2 weeks, we had the underlying infrastructure, we had a lot of the underlying concepts that would allow us to build that initial prototype that would make us go, okay, there might be something here. And those principles that existed, the idea that our data requirements form a tree, the design around asynchronicity and the striving for single sources of truth, that's very clear in the GraphQL spec and in the design of GraphQL implementations. You know, the data requirements form a tree. I don't even know how to expound on that. That is just so tautological in GraphQL. It's, you know, that input query is a tree. The design around asynchronicity, the idea that in the executor, yeah, everything could be asynchronous and we have to handle that. This idea of striving for a single source of truth, which, you know, the resolvers allow us to very cleanly map and say, every time I'm fetching a user's name, it goes through this method. And I know that because I wrote it right there. Last year, not on this stage, on the previous stage, the one that only fit 400 instead of 800, Nick Schrock talked about GraphQL native servers and the need to design our servers around GraphQL. And I think these 3 principles really sort of define, in my mind, what a GraphQL native server would look like. They have to answer all these, because if they don't, GraphQL is not going to click. It's not going to fit in because GraphQL is designed to work with a server that thinks like this. And what the shape of that server is going to completely vary. You know, I will happily expound, if you find me in the room over there, on the benefits of a monolith. I'll talk about that all day. I love them, but it doesn't have to be a monolith. You can easily hit all 3 of these principles with a non-monolith, and plenty of people have. And so I think that, to me, is really key, is when we talk about this GraphQL native design, we want to make sure that we're hitting the underlying principles. One thing I'm really excited about today is the fact that I spent all this time talking about the creation of 2012 era Facebook server architecture. There have been 7 years of evolution since then on that original GraphQL native server. And so the fact that we've got 2 talks from people who are working on Facebook server during this conference gets me really excited. And I'm also excited for our next talk, because in addition to talking about GraphQL native servers, we can talk a little bit about the clients. We can talk a little bit about the original GraphQL native client, the Facebook iOS app and the Facebook Android app. And so I'm excited to hand it over to Matt Mahoney, who's going to be talking about how to scale them. Thank you.
Let's get this set up. Oh, there it went. Thank you. Is this on? Got this? Cool. So, hi everyone, thanks for coming out, thanks for attending. We as engineers usually need to build new things. So I'm going to give all of you a task. This task is to build a really fancy profile UI. First time ever you're doing it, you've got this brand new shiny app. You're responsible for everything in it. So we're here at the GraphQL conference. We're used to thinking in GraphQL, or we'll get better at it over the course of this conference. Well, when we think about what we need for this basic UI, we need some JSON response that has a picture and the information about the person you're viewing. So in my case, we can tell I'm clearly not a designer, just like Dan. So given this app, we're going to need to scale it over time, assuming we're successful. So at the start, we'll probably just have one fragment. One person will be building this out. They'll understand the server. They'll understand the client. They'll know intimately what the code in PHP or Ruby or whatever your server's written in does in order to get a picture. They'll know intimately what the description is all about. And over time, as the app gets more and more success, as people start using it, we'll hire somebody else. All of a sudden, you're a tech lead. So you're responsible for making sure the app or the profile UI is really, really good. And somebody else on your team can take over the responsibility for imaging, for fetching images from a cache, for making sure that they can actually render the image consistently everywhere. I don't have to worry about that anymore. I'm the tech lead. And again, we scale again. Now we need to add more features into our app. We need some sort of, in addition to our profile, we also need to worry about other verticals like groups. So a group is very similar to a profile, except for instead of having an about, it has info, and that info might have tons of different information, but it might be a nested tree. In this case, we can see our example group is all about geese. And these different sections are going to want to share a lot of infrastructure, share a lot of components across the app. So if I'm building out a new group section, I don't want to have to worry about how do I fetch an image from our CDN? How do I render that? that should be somebody else's responsibility, somebody who's actually good at that. And over time, we'll scale again. So we've seen tons and tons of success, and now we've got people clamoring for us to build more and more apps. The unfortunate thing here, as from an engineering point of view, is that oftentimes this means each app has its own designer, which means in one app, the designer is saying, everything, every single image needs to be square. We have to have this consistent user experience. So every single image must be square. And in the second app we build, the designer's saying, well, that doesn't fit our original design pattern here. So in our second app, we need every single image to be round. So we need a way to describe, yeah, we're reusing a lot of the same pieces, but somewhere in that tree of information, we're actually going to end up with something slightly different. So I'm Matt Mahoney. I'm a software engineer at Facebook, and I'm here to talk about scaling your GraphQL client. So some of the things we're going to talk about today are models. How do we actually model this data? How do we get the models to scale with the size of our app, our organization, our company? So we'll talk about basic JSON models. We'll go into type models and how you can represent models from your schema. We'll go into response models. So given the tree that we're getting back from the server, how can we access that tree? And then we'll dive into fragment models. So how can we encapsulate just the data we need for specific components? And this really is the history of how Facebook has worked with our native clients to figure out how we're going to model our data, how we're going to access them in the apps. So the first thing you want to do is just use JSON. Like the spec says that your GraphQL server is going to return you JSON. This is great. Everybody knows how to deal with it, right? So if we look at this nice schema, we've got some user with an about and a picture. We've got an image. And we'll use some fragment to actually get the data we need for our profile UI. A JSON model basically just ignores all of that. We have getters that let us access by key. Usually, if we're in Java, there will be some third-party JSON parsing library that we can import. And then there will be some values on it that let us say, this key we're expecting a string from. This key is going to be another JSON object, etc. So this is actually a pretty good thing at the scale of one person early on in your app, because it's easy to iterate. The thing that you're taking in is just a library for JSON. And if we're going to use it, we just call the natural JSON getters that already exist in our JSON library. So to render that image, all we need to do is ask for it in JSON form and then get the URI out of it. But this is going to happen a lot. We have some issues. So one of the immediate ones is that we've got a typo. I forgot that we actually encoded the URL to be URL, not URI. And that's really hard to see, especially on my computer screen, but up here as well. What's the difference between an L and an I? And we don't really get any form of type safety. So we're getting this about as an integer. That makes no sense. From the server, it's going to be a string, and then our JSON is going to give us something, maybe. Maybe it'll coerce it. Maybe it'll crash. I don't know. And again, we've got this problem that I'm going to call underfetching. So we want to get the information so that we can render that I'm not a designer about information, but we never actually asked for it. If we don't ask for it, we're just going to get some null value instead of what we actually want. So underfetching means that we are using the data in our component, but we never got it from the server. And the corollary to underfetching is overfetching. So it's very easy, especially with JSON models, to ask for more data than you need. Some people want to, ask for more data because they might need it in the future, but every single field that we ask for is execution time on the server, and also, possibly more importantly, is data that we're costing our users. So if we can do anything to prevent asking for more data than we actually need, we probably should try. And JSON models, we don't really recommend at large scale. So we expect people using JSON models to own the schema, own the client, really own the whole code that they're working with. They should be having well-defined stable types. It's not a lot of iteration. And at Facebook, we do use JSON models quite frequently, but usually it's in the form of things like tooling or tests, things that when we change how they work, get run in automation or will immediately find. We don't want things that when we change will lead to bugs in production. So if we're not going to use JSON models, maybe we can generate something that has getters, will prevent these typo bugs, will give us better type information. The obvious thing to do is to use type models. And the basis of type models is the schema that we generate. So you've written up your server resolvers, you've got all the fields that you can possibly access, and these fields then produce the SDL. We can use these to generate Java classes in the case of Android, or iOS or Objective-C classes for iOS, and provide getters for each field on the type. This is just a one-to-one mapping. If the field is nullable in the schema, it'll be nullable as a getter. If we try to fetch it, maybe it won't actually be there. That's okay. So this does scale pretty well to like about one team. Over time, though, so doing it directly on the schema, we hit a problem very, very quickly. And that's we can't even alias fields. So I, as the tech lead, assigned somebody else to create the image, and they decided, well, this is a square picture, but the picture's really little for the profile, so we're just going to name it Lil Pic. There's no way to represent that. I have no way to get that picture, and I can't tell whether I'm getting that little picture or big picture just from the model itself. So we need to do something a little bit different. At Facebook also, this just wouldn't scale. We have 30,000 types in our schema and 200,000 fields. If every single Facebook app had to take in that entire schema, 30,000 additional classes shipped with our Android app, that would be completely ridiculous. Like, we'd be wasting people's data before they even open the app. So instead of having the type models be based directly on the query, or based on the schema itself, we can base it off of what we actually ask for in the scope of the app. So in this case, we generate much smaller type models that have a one-to-one mapping with what we asked for. If we have an alias, we get it, but if we have fields that came from somewhere else, some other query unrelated to my profile component, I'm going to get those in my type model as well. So to use it, you just pass around your user model, your image model, pass it around throughout the app. To render the picture, we can just have an interface has pic model that so long as we implement, we will be able to pass down into that renderer. So this is great. We now no longer get typos. And we get type safety, right? Because you can't act like the fields that you're going to get, if it says it's a string in your schema, you're going to get it as a string. But that's not totally true. What do I mean by this? So there are instances in the GraphQL spec when even though something says it cannot be nullable, it can end up being null in your response. Type models, because they work on the scale of the entire app, have no way of differentiating those two states. You have to choose one, even though in one response it is non-nullable, in the other it could be nullable, which means when I try to access my URL, I don't actually render anything. So we still also have the underfetching problem. I didn't point it out, and you probably didn't notice, this is something I probably wouldn't have noticed, but we never actually are asking for the image fields. Even though the type that we have, the user model, has that little pick field available on it, we only are asking for the about field, and when we try to access them, they'll be null, and in this case, we assumed that the image was non-null, and we'll probably get a null pointer exception and crash the app. And again, we still can't really solve overfetching. If I delete the big picture here, I'm not using it directly in my component, but somebody else might be using it, and I have no idea who that is. Every time I delete some field, I have to go through and hunt through the entire app and find every usage of it in order to remove all that code to allow the app to even build, even though nobody else was ever actually fetching that field. So type models also don't scale well to many teams because you have to choose, do I have one gigantic type model library, or do I have a type model library, per team? How do I mix and match this? You have to make a choice, and any choice is basically not great. And again, I talked about builds breaking. Any change you make to type models can affect some other team's code. You have to rebuild that code, otherwise their build is broken without you knowing. This does scale. This scales actually quite far. I wouldn't recommend scaling it that far, but Facebook still uses type models quite frequently. The models scale with how widely used they are in the app. But to keep it correct, it requires a lot of manual testing because you can delete a field and not know what the downstream effects are on all the other queries in your app. So we know we don't want to use type models. What can we do? Well, there's another kind of model called a response model. The core idea here is that GraphQL responses form a tree. They form a tree of information, and we want to ensure that we have access to all the pieces in that tree of information. So for response models, we create one class or one interface per fragment. We use interface inheritance to represent fragment spreads. So the user profile has access to little pick because it extends square pick. And little pick, so square pick.littlepick, has access to the URL field because it extends core image. This allows us to scale the app to many more teams because we know that the data that I have access to is only what I've actually asked for. When we're using it to pass some response model into another function, so I've got some profile and I want to render the square picture of that profile, I just get my model and pass it down. Because I used interface inheritance, I know that I am a square pick, this leads to a really nice property. With response models, it becomes impossible to underfetch. If you don't ask for the data you need, it won't be there in your response model. If you don't spread all the fragments for all the information that you actually use, it'll be a build time, compile time error. But we still don't solve overfetch. Again, we've got this big pick here. We're asking for way too much data that we don't really need. This other person on my team just did not get the brief, didn't realize that he never needed to ask for it. But because we're not encapsulated, we can still cause problems in the app when we remove important fields. So in this example, we're removing the URL from the core image. The core image component, the team responsible for rendering images, caching them, getting them from the CDNs decided URLs by themselves aren't what they need to render an image. Instead, they need some smart URL, they need more information or different information. Well, unfortunately for that core image team, every team in the entire app has started to depend on them because they're the source of truth. And other teams have started to do funky things with that URL that's part of core image. No other team's fragment includes URL, but because the response model gives you access to everything via inheritance, they're using it. And they're making product decisions based on it. So when the core image team removes the URL, all of a sudden, products start breaking throughout the app. That core image team now needs to go to every single product that uses their code and fix it up. This greatly slows down infrastructure teams. If you ever have somebody relying on your code, this is not a great state to be in. At Facebook, it has led to situations where modifying a core fragment that's used everywhere in the app has led to hour-long builds. Nobody wants that. And so we need some other way of doing it. Additionally, response models they scale really well in one application, but if we have two applications and we've got the two designers, so remember we had one designer say all our images need to be square, and we've got another designer that says all our images need to be round, there's no way to encode that besides maybe overfetching. Maybe we fetch both pictures, and at runtime, we decide based on the context what to do. It'd be a lot nicer if we could use only that data we actually need for the app that we're running. We don't want to pull in information from the Squares app just so that it can share the core image component with the Circles app. So these response models do scale. For our Facebook native clients, we quickly learned that type models were problematic. We quickly moved to this response model view of the world. And most of our models at Facebook today in our native clients, so iOS and Android, are these response models. So we want something more encapsulated, more modular, something that can really scale not just with one application, but across many. Because, again, our company has been so successful that we now have shared infrastructure across applications. Bring in the fragment model. So a fragment model is very similar to a response model, except every fragment that you spread acts as a black box. Instead of using interface inheritance, instead of getting the fields implicitly because somebody else called them, to pass yourself to a function expecting a different fragment, you need to do an explicit conversion of some form. So in order to pass my user profile with the fragment that I spread into the picture rendering method, I need to do the conversion. I need to say dot as that app pic. So this, in our view, does actually scale very well to many apps. As an example of usage, you can convert yourself between fragments, and one nice property that this allows that is a little bit more correct actually than response models is your fragments that you convert to can end up being null. So the core image had an @include if. If we didn't actually ask for the data from core image, well, why are we trying to render that component? We should only be rendering the core image component if we actually got that data back in our response. This allows us to do fun things like if you're getting a union of types and you're spreading a bunch of concrete types, you can ask, okay, am I this concrete type? No, render something else. This isn't easily possible with response models. So we've solved typos, we solved type safety, we still have underfetching solved, but it's still possible to overfetch. We still haven't statically at build time prevented you from overfetching. But because we're well encapsulated, because you can't access any child fields, in code review, when I see somebody has their GraphQL fragment has a field they're not using in their component, they can delete it because we know it's not going to affect anyone else. Every other product in the app is using my fragment as a black box. This drives down our build times. So instead of being big O, all the queries that use the core image fragment, it's now just the core image library that needs to be rebuilt when I modify that fragment. Because we can safely delete fields, we reduce our overfetching even if we can't statically eliminate it purely through the models themselves. Fragment models also scale pretty well to many apps. If each app has its own design team, we still, as engineers, usually want to reuse the core components. Because the models are black boxes, because we enforced encapsulation, we can inject app-specific fragments based on the context that they're running in to match the design or the needs in a specific application or context. And generally, at Facebook, we have not found pure true fragment models to have major scaling problems. They add overhead. They're more complex to generate than raw JSON or type models or even response models, which is why our natural inclination was to build up those other kinds of models first. But we found first through iteration, actually through Relay. Relay was built from the ground up with this idea of using fragment models first. They learned from many of the mistakes that we'd already made in our native code and are still trying to unwind in Facebook's core applications, where Relay always used fragment models. And in our native code, in Objective-C and Java, we're starting to do that massive migration. We're starting to try to move the mountain to move us away from our type models and response models to true fragment models.